So yeah, but thank you very much for inviting me. The F electrons will not be very much in the center, but I thought I have to show one slide about F electrons. Otherwise, I miss the topic of the talk. So I would like to thank Alex, Darius, how do you pronounce it? Peter. Okay, and Peter for the invitation and for the perfect organization. And yesterday I figured out that even for the salad dressing they found something which is related to the workshop. So what I'm going to talk about is essentially say a little bit on the Raman experiment, but we had already many talks on that. I have a little bit on F electron systems as mentioned, and I mainly speak about fluctuating conductivity in the iron arsenides because that's our main business we're working on in the last couple of years. I can take one. So the Raman experiment is very simple. You have polarized monochromatic light going on the sample, and you collect the energy shifted light via some lenses, and you analyze also the polarization states of the scatter light, and you find you analyze the light with respect to the energy shift transferred to the material, which is given by capital omega. And so this is how it looks like. It's one of the machines. You have a laser, you have the light coming in here that polarizes. You go into the crystal from below and you collect the light along this axis, go into the spectrometer and detect the light here with the CCD. And using this type of is the microphone working or not?
Maybe you need to switch it on.
Yes.
Maybe I switched it on.
I mean, typically,
Is there a green light on the top?
but there is no green light.
Yeah, you got it switched on. There you go.
Now, it's not much more audible. Okay, so you can look at all these different types of excitations, and what is very important is the selection rules, as we heard many times. I focus on electrons because a little bit on amplitude modes and fluctuations, and that's the whole thing. And since you have two dipole transitions as opposed to one in the infrared, and you can adjust two polarizations independently, you have much more degrees of freedom with the selection rules. You can project certain lattice vibrations, you can project parts of the magnon dispersion in the orbit transitions, which you have just heard in the previous talk. You can project parts of the Fermi surface in metals, which means you can selectively probe, for instance, the energy gap or also the relaxation in the normal state. And the essential trick is to map the symmetries and the photon polarizations. And here I give an example for the D4H group, and we have seen this many times. So you have your polarization with respect to the crystal system, and here in the D4H you always project two symmetries, and in order to get out the symmetries you have to make proper linear combinations. And then in addition you have this chiral symmetry, which is basically lifts the XY symmetry, so XX minus YY, sorry, XY minus YX is different from zero, and you can do that by doing certain polarizations. So the first part is on these F electron systems, and these were tritellurides, which we did in collaboration with Leonardo De Giorgi and Michele Lavagnini, and that's my people, it's Hans Eiter, Thomas Böhm, and Baum, so they will also be, they did lots of work also on the big tides. So here you have the tritellurides, you have slabs of only bilayer of tellurium plane, and you have this rare earth telluride slab in between. And we are first focusing on these properties of the rare earth cerium, and we have got all the introductions, so I'm just flashing what is coming out. So this is so that's much more benign than apparently than the cerium hexaboride. So you get all these crystal field excitations at high energies and partially at low energies. And one of the incisive ways to distinguish between all the phonons and the amplitude modes you see in these charge density wave-oriented systems is looking at this A2G symmetry, which is essentially a transition between states with the appropriate angular momentum, as we have heard in the last talk. So meaning if you look at these excitations here in the proper energy range, you can essentially get information on the side symmetry and many other things. So here are the, once again, you see that this is a low symmetry position, therefore you get lots of, you lifted the Cherenkov was completely. So that was just my excursion into the F electron systems. Now we have something different. This is the erbium tritelluride, which has nothing to do with F electrons. It's just about the charge density wave in the tellurium bilayer. And Brian Raven did a lot of work on that, and in particular with pressure. And he found, he and his group, they found superconductivity at high pressure and low temperatures in the range of 2 to 2.5 K. I'm not talking about superconductivity, we didn't see it honestly. But what you can do is the following: you get this amplitude mode. This amplitude mode is essentially a longitudinal fluctuation of the order parameter in the charge density wave state. You can either go through the transition by varying the temperature, or you can go through the transition by changing the pressure. And this is one of the direct indications of how the charge density wave reacts to pressure. And if you plot that as if you plot the transition temperature, actually the temperature at which this mode disappears as a function of the pressure, you see, you find the erbium tritelluride disappears at 2.5 gigapascal. I mean, we didn't unfortunately see any type of superconductivity. So, but this all now this terminates the excursion into the F electron systems. Just shows that you can do lots of things. I mean, you can look at amplitude modes, you can look at acoustic field excitations. Now we are doing something different. We look at high TC superconductors in the superconductivity in the iron-based systems. These are Thomas Böhm and Andy Baumgarten, and this was a previous student, that's Florian Kretschmer, and the other one is Bernhard Buschler. So, I mean, what you're always interested in these superconductors is the nature of the superconducting state. And of course, many people say this is not conventional with phonons as usual, with a like niobium tritium. So it is different from that, and it might be related to the phase transitions and also at the into magnetic spin density wave state. And the question is there an interrelation between superconductivity and spin fluctuations? So that's the main topic of the rest of the talk. So we start looking at the fluctuations. But before we do that, I just give you once again a little bit of a primer on the selection rules. So we have this type of structure. We have this is the iron plane here. You have always to take the proper coordinate system if you want to get out something. And since all these bands in the iron arsenides are in high symmetry positions, you can select, you can look at the bands differently by just adjusting the polarizations of incoming and outgoing light. So this, for instance, is seen in the B1G. B1G is now not the crystal system but the iron plane, because all the bands, the electrons are coming from iron orbits. The A1G projects a central band, the B2G is not very sensitive, it just leaks a little bit from all bands all over the place. So what do you expect if you look at electrons? We have seen lots of crystal excitations from on. If you look at electrons, you just know from your textbook that the response of a material with impurities looks like a Lorentzian, right? And the intercept to the ordinate at omega equals 0 gives you the transport lifetime. The width gives 1 over lifetime. If you want to go to the Raman, then of course you have to multiply the conductivity with the omega, and you get the imaginary part of the lifetime. Now the peak is the 1 over tau, and the tau itself is the initial slope. So if you have the initial slope and divide it by 1 over the initial slope, you get the same thing as you would from the conductivity. So this is I mean, this is very general, and I mean, it's also a general statement. If there is no impurities and if there are no interactions, you don't have any scattering. Now the question is, why do we do Raman if we get the same result from the infrared? So the reason is we get selection rules in the Raman. And I was showing the slide before that the selection rules allow you to look into different parts of the Prima zone, also with the electronic Raman scattering. This is essentially because all the isotropic response in the charge system is screened away. Therefore, you get selection rules. So now we look at the Raman response of this cobalt dot materials. The cobalt dot materials, the phase diagram is shown here. They have this small wedge of a nematic phase, and we are going through this nematic phase here at finite doping. And I show you that the selection rules really give you different things, right? So you start at room temperature, and the spectra, except for the phonons, look very similar in the two symmetries. Then you start cooling down. Nothing spectacular happens until you reach something like 200 K or 175. Now, the point is, the chain continues pretty much without spectacular changes, but here something is growing out in the D1G symmetry. And if you go to low temperatures, you get an extra response here, which is superposed on the normal conduction response, right? And now we continue cooling down, and then the intensity is being reduced here. Nothing happens with the A1G on the whole bands. It's getting more reduced, and then all of a sudden the peak disappears here. You see that much better in the next slide. And you get an extra response on high energy, and you get a reduction on the low energy side, which comes from the gap in the spin density wave. So you see the temperatures are indicated here on the right hand side. And, I mean, I don't have enough time to show you all the movies which we have to determine these temperatures, but we can determine these temperatures intrinsically via the observation of the sample within a precision of something like a fraction of a Kelvin. So we know very well where we are in temperature. So and that's the response then at low temperature. Now, what we do, we look at this initial slope I was explaining a couple of slides ago. In the A1G, the whole bands follow pretty much the resistivity. So you see, you can measure the resistivity using Raman scattering. But in the B1G symmetry, at the electron bands, essentially electron bands, you find a coincidence only at high temperature, and at low temperature there's a crossover. It goes down, and we find a relatively well-defined temperature TF, which marks the part of the temperature dependence which is described by the resistivity, and another part which is not yet clear. We do now the following. We can go to this temperature TF, determine the spectrum at TF, and subtract it from all spectra at lower measured at lower temperature. That's what you get out. So you get an extra peak which grows up, changes slightly in with temperature, increases quite a bit, and this upper part, the green part, was known before, and by all these authors. And the point is, there is no consensus about the interpretation, I should say. So it's so Choi et al., that's Peter Lennon's group. They say it's essentially the central peak from the fluctuations, which is probably gets relatively close. And Jan Gallet and his people, they say it's coming from charge fluctuations. And Bernard Thorsen it's from Dirk Bloomberg's group, that they think it's a kind of a Pomeranchuk fluctuations in a Pomeranchuk type of fluctuations. So now, what we do next is we go through this nematic phase. In the nematic phase, we observe that the peak doesn't change very much. What is the meaning of the peak? That's something we see in the next slides, but let's just look at the experimental observations. The peak doesn't change, it just becomes weaker and weaker and weaker, and then at the transition into the spin density wave phase, this is the light blue spectrum, the peak completely disappears. So that's the new part that is in this work which has been published recently. So now we start with the analysis. If we have fluctuations, we we have two possibilities. We can look at fluctuations at q equals to 0, that's the Raman, or we can look at two fluctuations with opposite momentum. If you have two fluctuations with opposite momentum, the total momentum transfer to the sample is 0, and this is compatible with the Raman experiment. And this is why we started analyzing this data here with this type of diagrams in collaboration with a group in Rome and people in Karlsruhe. And so what we get is the following. We get the proper selection rules for q equals pi 0, meaning this is the direction of the spin fluctuations. We get the right shape taken just from this paper. And in addition to that, we get the temperature dependence. The peak doesn't disappear in the nematic phase. So if it is fluctuations from, so the orbital fluctuations and all this type of fluctuations freeze out at the transition temperature into the nematic phase, because these are generically nematic fluctuations, but the spin fluctuations should not freeze out before you enter the spin density wave phase. Imagine the following: you are at a critical point of a gas. I mean, you know all these movies from YouTube, for instance. You have critical fluctuations above the transition temperature, above the critical point, and as soon as you are in the liquid phase, the fluctuations disappear all of a sudden, and you just get a surface of your liquid, and this is exactly this type of fluctuation what we have in mind. Therefore, if they disappear, they can disappear only in the ordered state of the underlying ordering mechanism. And this is why we believe this is coming essentially from spin fluctuations, which does not mean that other things cannot fluctuate also, but the dominant part, the driving part, is the spin fluctuations. So this is one part, and you see the shape, the selection rules, and the t-dependence kind of made us believe that we are dealing with spin fluctuations. Second thing is now superconductivity I'm talking about, and we get also some indications that the spin fluctuations play a role here. So, but first, before I enter into this business, I show you what you expect in a superconductor. So normally you have one conduction band to make things simple. If you go into the superconductor, you have particle-hole mixing, so you just reflected about the chemical potential, and then these electrons start talking to each other, and you get a gap. This is essentially what drives the phase transition, and you have particle-hole mixing here, and then in addition you get Cooper pairs at the chemical potential. And if you do Raman scattering and infrared absorption, you get totally different things. In the normal state, you got exactly the same thing, modulo factor omega. In the superconducting state, you get coherent superposition of the response from the condensate, so from the Cooper pairs, and the response from the excitations across the gap. And therefore, you get a divergence in the Raman, and you get an onset in the infrared just above the gap. And so now we are looking at this potassium doped side. So we are not on the electron doped side any further, we are on the potassium doped side. The reason why we do that is in the potassium doped side we have a really clean gap, and you will see that in a minute. And so you see the spectra which we obtain from the from this material. So you have different symmetries. Once again, of course, you have different phonons. The response doesn't look spectacularly different if you are close to the superconducting state. But then you go to below superconductivity, and the first observation is you don't get what you learned from what I was just explaining. I mean, the bad messages you don't get the sharp onset, but the good messages, there is at least a gap, right? Below some certain energy, you always find a reduction of the scattering intensity, and in addition, you find some extra intensity at around a couple of hundred wave numbers. What we do now is, in order to get rid of the phonons, we subtract the light blue from the from the dark blue or from the magenta spectra in order to just isolate the electrons. That's what you get in the A1G symmetry. So this is the gap, this is the onset, and this is the more or less the square root decay on the Heinrich side. So it's not so different from what I was showing before. Then the other symmetry, you get also a gap, but you have a couple of states inside, but you get a peak which is at a similar position. Now, this one is totally different from all the other symmetries. First of all, you get a peak which has missing a lot of intensity on the high energy side. The onset is approximately the same as in the blue and the green spectrum, but you get a sharp mode inside. So this is basically the topic of the last couple of minutes I want to talk about. Now I just repeat what is going on. The first thing I have to say, if you look at superconductors, you normally have a single band and you have intra-band interactions which make the whole material superconductor. Here, in the iron arsenide, the main interaction comes from interband interaction. So this has been shown by many people, and I think there is quite some agreement on that. That interactions between the bands is stronger than the interaction on the band. So this is basically giving you the pairing rule for the Cooper pairs. And then you get something else. You can also have an interaction between these two electron bands. And the interaction between these two electron bands, and since it is in the spin channel, it's repulsive, so it frustrates the other channel. So I mean, if you crank that up, at some point it won't be superconducting anymore, but as long as it is superconducting in the ground state, as long as the blue one is stronger than the red one, you just expect an exciton inside the gap, which is pulled down from the gap energy a little bit. So, and the energy which the energy with which you pull it off the gap is just encoding the coupling strength in this red channel, in the D channel. So this is nothing I invented, this is something really old. And that was derived by Bardesis and Schliefer in the 60s, and then Klein and Dierker were talking about it, and Monin and Zawodowski derived it again in a way that even I can understand it. And Calapino and Devereaux finally did it for the iron pnictides in a multi-band system. So all these papers here are of course on a single spherical Fermi surface. What you have to do is you have to take into account the interaction between the two types of electrons you have on the side, and what technically it's called a vertex correction. If you do so, you can explain this missing intensity on the high energy side. But Thomas Grims started with the analysis on a realistic 3D band structure, and he was playing around a little bit with the gaps, starting first with this type of spectrum, then with the A1G spectrum, and finally, I mean, to make everything consistent, he calculated the B1G spectrum, and he is missing intensity and can't explain the in-gap state here. I mean, it's so sharp that you cannot interpret it in terms of the usual gap rating, right? But then, if you switch on the final state interaction between the electrons of a broken Cooper pair, you get a relatively good explanation, right? You come intensity from above the gap into this sharp in-gap mode, and you can derive the coupling strength, the relative coupling strength in the E-wave channel with respect to the ground state, and all these type of considerations lead to a ratio of 0.6. This is very large, right? So if you just crank it up a little bit, then you get an instant, the ground state becomes unstable. And therefore, it is interesting, do we reach a state which is really unstable? And therefore we looked around optimal doping and looked at a couple of other doping levels around optimal doping and find the following observation. Now, all these different spectra in the P1G channel are plotted as a function of the normalized energy. So we normalize the energy with respect to the transition temperature of the various samples. The first observation is the pair breaking part is essentially staying close to it. So it's between 6 and 6.5 units of KTC, indicating strong coupling. This, I mean, 3.5 is the generic value you would expect from BCS. If you have something which is larger, then you know you have a strong coupling superconductor. But the other thing is this sharp in-gap mode starts moving really strongly away. Meaning, in other words, if you go to higher doping levels, you find that the coupling strength in the subdominant channel is much stronger. It's becoming stronger and stronger if you go to the overdoped side. So this is what we have at the moment, and we have another strongly doping-dependent peak here, but we are still working on that. So it's just a state-of-the-art report what I'm giving here. So the take-home message is you find an in-gap mode which depends strongly on doping, indicating that if you go to the overdoped side, you have increasingly strong subdominant channel in this type of materials. We were very lucky because we have clean gaps in this type of potassium doped iron arsenide, and so we can in fact see these modes inside the gap. You need a clean gap to see, but apparently this works out nicely in the potassium doped samples. So that's all I have to say. And to summarize briefly, so we see apparently in-gap modes in the potassium doped side, and we see fluctuations on in the cobalt doped side. Just recently, we also looked at the fluctuations in the potassium doped side. They exist, but they are much weaker. But they are still around, in spite of the fact that there is no nematic phase. So, in other words, there are fluctuations all over the place in these materials. What we don't know yet is to which extent they can be related to the superconductivity. However, this type of in-gap modes indicate that the spin fluctuation scenario for the pairing is more likely than other explanations, because otherwise you wouldn't get this in-gap mode in the P1G symmetry. So that's all the people who contributed. That's quite a few, and I'm very grateful to those who contributed to the funding agencies, and thank you for your attention.
Okay, questions? Yours.
I have two questions. Both are interpretation, because the data is entirely consistent with what we see. On this last part of the superconductor part, so there's no doubt that there's a collective mode in the gap. Right? The question is whether this is in particle-particle channel or particle-hole channel, whether it's Bartazzi-Schrieffer-like or it's a collective mode arising from nematic phase, which basically would mean that the roll feature, the ODAM feature that you showed in the earlier slides in P1G channel, when gap opens up and relaxation is removed, becomes an in-gap collective mode, but essentially it's a nematic, has a nematic origin.
Well, I mean, in the potassium doped samples, at this doping level, we don't have any nematic fluctuations.
We see, of course, not as strong as over there, but again, in the same, by doing this very similar experiment, we do see quasi-elastic scattering, which is perhaps not as strong, but clearly is present, and then it disappears at the transition, because there is no really deep structural transition like that.
Yes, we can talk about your results, which were never in the public domain. on this compound later on.
Okay.
But I mean, let's focus on what we have here.
All right.
And what we have here is we don't see fluctuations above the superconducting transitions. So, and I mean, it's possible that you can see them, and if you change the laser line, and that might give different resonance effects. But here I cannot talk about it because I simply don't know it.
Okay, the second question is again interpretation, giving kind of a strong preference to magnetic fluctuations being driving the nematicity.
Mhm.
What your data also shows consistently is that there is a enhancement of the static susceptibility, in that case your flow, towards the structural transition. Then at structural transition, the enhancement stops, right? It basically stays the same or goes slightly down, and then at the Neal transition, magnetic transition, it raises up. So there is no question there is a fluctuation between Tm and Ts, but the critical type enhancement is slowed down or stopped below Ts. That's what data says.
It goes down. I mean, you have a peak at Ts,
Right.
and it increases from either side.
Right. So it goes down. So therefore, the structural fluctuations certainly are important and contribute as well as the magnetic, because up below Ts, it doesn't keep increasing, it certainly decreases.
What does it invite by vacuum? Does it argue in favor of structural fluctuations?
Well, you correctly list that orbital fluctuation, maybe different surface fluctuations, and magnetic fluctuations are all in the same channel. They all mix, and strictly speaking, we can't even say who is in driving seat, as some people call it.
Well, I mean, but the structural fluctuations and pneumatic fluctuations should disappear at the pneumatic transition, right? And not the magnetic ones. That's what I.
That's right, and magnetic are still keeping driving it, therefore it doesn't drop like a rock at Ts. It just goes down because it doesn't have. So the point is that above Ts, pneumatic, whatever they are being coming from orbitals or magnetism all have power. Below Ts, this weakens, and therefore
But I mean,
the critical
you
behavior
would have
stops.
a jump at Ts, right? If you would have a strong contribution from other types of fluctuation, you would
They're all
have a strong
coupled to
jump.
each other. They're all coupled to each other. It's difficult to say that it's.
You should have a jump, right? If they die out, right?
Right. Do we have other questions? Okay, let's thank our speaker again.